So good morning, everybody. I hope that you're all doing really well, especially during this pandemic. Um, so before we start, I'd like to thank all of you for being here and also the organizers of BDHI 2020 for bringing us here. Um, okay, so this project is in medical informatics, and the goal is to predict whether a specific type of ophthalmic device, the glaucoma drainage implant, uh, will be successful or fail. This project is a collaboration between the Department of Math and Computer Science at Fontbonne University, the Department of Ophthalmology and Visual Sciences at Washington University, and the Department of Mathematics and Computer Science at Baerveldt University, all here in St. Louis in the States. So first, let's start with what is a glaucoma drainage implant? First, glaucoma. Glaucoma, it's a family of eye diseases um, that affect the optic nerve. Um, the end result in many cases, unfortunately, is blindness. And unlike in the case of cataracts, the blindness caused by glaucoma is permanent. There's no going back. Um, the diseases have different mechanisms, but they're almost all associated with increased eye pressure or intraocular pressure, pressure inside the eye, um, as you can see in the diagram here. So because there's so much pressure, it can be helpful to reduce that by allowing aqueous humor, the fluid inside, some fluid inside the eye to flow out from the anterior chamber to the outside of the eye. That's what glaucoma drainage devices do. At the end of the day, though, they're just synthetic implants, and they can be fragile. If the implant becomes detached or if it gets blocked, then it will stop working. And the effects of this, depending on the type of glaucoma, can be quite severe. Sometimes it may simply lead to the disease getting worse. Other times it could be a medical emergency in and of itself. It's important to keep in mind how glaucoma drainage implants fit into a patient's overall treatment plan. Ophthalmologists don't normally start a patient off on a glaucoma drainage implant. These are normally put in patients who have tried drugs and not seen recovery, who have had other surgeries and those haven't worked either. And by the time they get to this stage, it's one of the few remaining options. And this makes predicting whether the implant will be successful all the more important. By this stage in the disease's progression, a lot of things are going on, and it can be difficult to predict which implant will work best. So our idea, what if we could use machine learning to get a more like numerical perspective so that doctors could take data available on a patient and imagine putting each implant in the patient and say for each of these implants, how likely is it that the patient will see an improvement, and pick the one that works best on a numerical basis. Now, because this exact prediction task hasn't been studied before, we chose to do a model comparison. So this means that we're comparing models to see which ones work best, how they work inside, but we're not actually choosing a final model to deploy. And we also used a methodology for validation that was very cautious. More on that later. Okay. So what did the data look like? We had both demographic and clinical data. This was all from an electronic health record system. And okay, so our demographic predictors were the patient's race, their age, and their sex. Within the category of race, we had 3 categories from the data, which were Black, White, and Asian. And okay, so here are the clinical predictors that were available. We had the diagnosis, the specific subtype of glaucoma that each patient had, the implant type, so whether the patient had a Molteno or Baerveldt implant, all of them had one of those two. Also, the size of that implant was part of the information available. We also knew the preoperative intraocular pressure, so the eye pressure right before the surgery, and the preoperative visual acuity. Another predictor was the number of eye pressure lowering medications that the patient was taking at the time of the surgery, and the number of previous ophthalmic surgeries that they'd been given. We also had the type of surgeries. Most important, though, are the labels, the target column. We had two possible outcomes. This was a binary prediction task, and these were that the implant failed or didn't fail. Now, in different studies, failure is defined differently. So this was kind of an important decision. In this case, we didn't really make a decision. We defaulted to the definition that our ophthalmologist collaborators had used in a previous study, which was that the implant is considered to fail if the eye pressure is greater than 18 millimeters of mercury at the last follow-up. The reduction in eye pressure between the first and the last appointment is less than 20%, or the patient had another eye surgery unrelated to normal maintenance. Like, for instance, it would have counted if they had the implant removed, or a new one put in, or a different eye surgery. But if they had only needed it to be like adjusted or something, that would not have counted as failure. So here's some more information about the patient's diagnoses and their treatments. As I said before, the 2 implant types were Baerveldt and Molteno. Both of these are non-valved glaucoma implants. That's one category. The other category is valved implants. And our diagnoses. So by far the most common diagnosis was open-angle glaucoma. I think, yeah, and the next most common combined mechanism glaucoma and chronic angle closure glaucoma. Okay, so how did we convert the data I just described into a format that is useful for classification? So the first step was temporal. many of the predictors came from the last appointment before surgery. Some of the data from constructing the target column came from either the first appointment or the last appointment, so there was an element of time there. Also, categorical variables were split into multiple binary variables. So what does this mean? Down the road, we're going to see that when we interpret the importance of features in the model, we're not talking about the importance of a category. For instance, we wouldn't talk about the importance of implant type. We would talk about the importance of individual types of implants, like maybe the Molteno at a certain diameter or area. And another step that we took was transforming some categorical variables into count variables. For instance, when we were tallying which patients had had which ophthalmic surgeries previously, we took a final step of summing all of the different surgeries into one column, so that we had a special column for the number of previous surgeries each patient had had. Okay. So next, the models that we use. To go in no particular order, a random forest is a good go-to classifier that you would expect to do fairly well on most tasks. Logistic regression, a very simple model that will give you a linear decision boundary, easy to interpret, and it's also used very often, traditionally, especially in medicine. And SVM will also give you a linear decision boundary. A decision tree, another very interpretable model working on the same principles as the random forest. A neural network, the most, I guess, flexible or complicated one here, just to kind of see how much could a more complicated model capture. So how do we train these? We were considering different feature subsets as well as different hyperparameters. The method that we used for finding the right feature subsets was recursive feature elimination. This is where you start out with all the features and try taking out one at a time until the accuracy until the change in the accuracy becomes insignificant. The fact that we were comparing different different hyperparameters as well as different feature subsets meant that we couldn't just use a single cross-validation loop. We needed to use, for each model, two loops. And one loop was for selecting the feature subset, and another loop was for selecting the optimal hyperparameters, and one was inside of the other. This is a visualization from the decision tree classifier. So the results. You can see here that logistic regression performed the best, followed by SVM. In another study, predicting surgical intervention, a separate team at a different university found similar accuracy. Now, this was for a slightly different task. This was for predicting surgical intervention and not implant failure. But this was also dealing with glaucoma patients. And so it's from the same domain. You can see from the fact that logistic regression and SVM did better, that it would seem that relatively simple models with linear decision boundaries may be the most useful for this. Another interesting result is related to the features that were important within each model. So for a given model, we calculated the feature importance for every feature, every column, using methods specific to the model, like the way that it was calculated for the decision tree is different than the way that it was calculated for logistic regression. And once we had the importance level, we ranked the features and created this visualization to show the most important across models. So here, red means that the feature appeared in the top 5 most important, and orange means that it appeared in the top 10 most important. We can see that some patterns appear across models. The feature that appeared most consistently across models was whether the patient was black. Some other features, age, this makes sense, IOP. This also makes sense as an index of the severity of the patient's disease. Some other important features, whether the patient was taking beta blockers, whether they had a specific size of the Molteno implant, 245 millimeters squared, and whether they had a previous cataract removal. So what does all this mean? For us, the importance of beta blockers and this specific size of the Molteno implant is a direction for further investigation. The explanation is not clear. This is kind of, I suppose, a new finding. And the significance of whether the patient was black may be due to genetic differences in wound healing and proliferation of fibrovascular tissue. This is consistent with observations in the ophthalmic literature. Okay, finally, this study had some limitations. The major limitation was the limited size of the data set with 62 patients. A future study might also include other types of data, like maybe biomarkers from blood samples or something like that, which has appeared in other studies of glaucoma. And finally, although our reported accuracy is comparable to similar results elsewhere, forecasting outcomes in glaucoma patients based on EHR data is still a challenging task, and high accuracy solutions have not yet been found.